This is absolutely incredible. Microsoft has released a research paper that discusses an LLM capable of truly self-improving. I know it might sound like sci-fi nonsense, but trust me, this is groundbreaking. The research paper is titled RAR Math. Small LLMs can master math reasoning with self-evolved deep thinking. And it's fascinating because the model uses its own thinking to make itself smarter. The paper states, "We present RAR Math to demonstrate that small language models, SLMs, can rival or even surpass the math reasoning capability of OpenAI's GPT 4.1. And here's the mind-blowing part. This is achieved without distillation from superior models. If you're unfamiliar with model distillation, it's a process where a larger teacher model transfers its knowledge to a smaller student model. The teacher model's knowledge is distilled down into the student model, which is then fine-tuned to perform similarly to the teacher model. For example, with GPT 4.1, we had the preview version, which was a fine-tuned version of the main model, designed to perform slightly below the teacher model's capabilities. Now, the truly astonishing claim in this paper is that RAR Math can outperform large language models without relying on distillation. That's huge! According to the paper, RAR Math achieves this by exercising deep thinking through Monte Carlo Tree Search, a method in AI that explores various possibilities systematically. The results are extraordinary. On benchmarks, the model improves the performance of the Guanaco 2.5 Math 7B, a 7 billion parameter LLM, from 58.8% to 90%, and the Guanaco 53 Mini 8B from 41.4% to 86.4%, surpassing GPT 4.1 preview by 4.5% on the USA Math Olympiad benchmark. Why is this significant? A common critique of smaller language models has been that their high performance on benchmarks stems from extensive pre-training on massive datasets. But here's the twist. This model doesn't just rely on pre-training, it improves itself to achieve these results. One of the most fascinating aspects of the paper is the diagram showcasing the RAR Math system, especially its Monte Carlo Tree Search mechanism. This self-evolution framework allows the model to think in a way that bootstraps itself to greater intelligence. On the left, the Monte Carlo Tree Search process is depicted. Here, the system explores multiple paths akin to a person contemplating the consequences of their decisions through a decision tree. The small language model serves as a policy to generate reasoning steps for solutions, and there's a preference model that further refines this process. This is basically something that verifies that each step is correct. I'll dive into this more later because it's actually pretty cool what they've done. Now, each one of these nodes you see here represents a step in solving the problem. You can see, for example, that this one is 0.7, this one 0.5, or whatever. These steps are the ones the model is going to take. The steps that are incorrect are assigned low values, and the ones that are correct are assigned higher values. This is where the system essentially assigns Q values to each step based on its contribution to the final solution. Basically, steps leading to correct answers get higher Q values, and steps leading to wrong answers get lower Q values. How this works is that they filter out these steps so that only the high-quality steps, the ones in green, are retained to construct the final solution trajectory. This process filters out and ensures that the AI trains on the best reasoning paths. What's fascinating about this is the self-evolution framework. While Monte Carlo Tree Search research is good, you need to add something on top of that to get a language model to improve itself. This is where the four-step process comes in, enabling the system to enhance both the policy, the small language model, and the reward model, the PPM. There are 4 steps to this process, and this is where you want to pay attention. It starts with terminal-guided Monte Carlo search, as seen here. At round 2, it introduces PPM-R2, which scores the results from the previous steps more effectively. The data generated in this round further improves the model. At this point, the model starts as R1, then gets upgraded to small language model R2. By round 3, the policies leverage the reward model to directly predict Q values during the search process, generating higher quality solutions and training data. This trains the next iteration of the model, small language model R3. Finally, in round 4, the final model emerges, continuing with an even stronger policy and reward model. This allows it to achieve state-of-the-art performance. This process is absolutely incredible. The model starts not knowing much and iteratively improves itself to become state-of-the-art. It generates all this synthetic data and can do so through this process. Looking at benchmarks, you can see how the model continuously improves its math reasoning capabilities through self-evolved deep thinking. By round 2, the model actually surpasses GPT-4. You can see what the base model achieves initially: a score of 58.8 in math, none on Amy, and none on another benchmark. It doesn't perform well at the start, but as the improvement process begins, outlined earlier, you can see it jump to 75.2, then 10, then 50, and then 35, showing significant improvement after round 1. We can see that the model is already surpassing GPT-4. Around stage 3, it gets even better, and by stage 4, it becomes state-of-the-art. This is where the model can even surpass 0.1. Remember, this model is based on only 7 billion parameters, yet it is outperforming state-of-the-art models. Of course, this is just one specific benchmark focused on math. However, when we consider how remarkable this achievement is, we can begin to imagine how incredibly intelligent these models will become. If a 7 billion parameter model can outperform RAR or GPT-4, imagine a mixture of experts utilizing such models. Models that are not only exceptional, but also capable of self-improvement. What kind of systems will we have then? Now, let's talk about how this model actually improves itself. At its core, the process involves generating solutions, evaluating those solutions, retraining on the best ones, and then repeating the cycle. This feedback loop continually refines the model's reasoning abilities. You might wonder, what about the unsolved problems? For problems it cannot initially solve, the model employs multiple reasoning attempts using additional rollouts or new random seeds until it finds a solution. This ensures that the model is always learning from its failures. And here's the incredible part. After the initial round, the model generates its own training data. This marks a major shift from traditional training methods, which rely heavily on distillation from larger teacher models. Self-generated training data eliminates the need for manual labeling or large data sets, making this approach cost-effective and efficient, particularly for specialized tasks like math reasoning. Additionally, the model isn't constrained by its initial training data, meaning it can continue to improve over time. In another paper, perhaps you've seen it, they discussed how OpenAI's 01 uses outcome-based reward models, which focus solely on whether the final output is correct. They contrasted this with process-based reward models, where the model is rewarded for each correct step in a solution, even if the final output is incorrect. For instance, when solving a math problem step by step, the model is rewarded for each accurate step it completes. However, for this particular model, even if multiple steps are correct but the final solution is wrong, it discards the entire process. Yet if the first 3 steps are correct and the last 2 are not, it still rewards the correct steps. This nuanced approach significantly enhances the model's learning capabilities. Now, what I found to be super interesting about this is that they actually changed the reward model. They used a process preference model and said that they introduced a novel training method that trains a process preference model by constructing step-level positive-negative preference pairs. Let me explain this for you guys. Basically, they've changed what they're doing here. They're using essentially a hybrid approach of process reward modeling. The PPM method, which is the process preference model, trains a model to guide the reasoning process by comparing these steps. This avoids assigning precise scores to the steps, making it more robust and reliable. This is the core innovation in the paper that's used to drive the Monte Carlo Tree Search process. Essentially, overall, when we look at the PPM, the process preference model, this is the backbone of all-star math, especially in the later rounds where it outperforms traditional process reward model approaches. They essentially use the process reward model initially for bootstrapping the model, but transition to more effective process preference modeling once the system matures. This hybrid approach actually balances the 2 benefits. Now let's look at the axes. At the bottom here, on the x-axis, we can see this shows us the sampled solutions. We can see as the sampled solutions increase, the accuracy of this increases. This is something we know, but this basically shows you how many solutions are sampled. On these graphs, we can also see the accuracy on the y-axis, and we can also see the different models. We can see that the green model, the All-Star Math model, shows its performance. We can then see the Quinn 2 models, the test of N, which is a different process. We can also see the 01 mini accuracy and the 01 preview on them, and we can see them across all these different benchmarks. Clearly, 01 preview wasn't tested on the Olympiad bench or college math, but for 01 mini, we can see the levels it reached in terms of accuracy. What's crazy is that as these sample solutions increase, the All-Star Math model manages to get smarter in its responses. Remember, this is a 7 billion parameter model going toe-to-toe with much larger models. This is something that appears to be true for all models. We can see that for all models, they seem to get smarter on the benchmarks as the sampled solutions increase. Of course, there is an initial jump. We can see that from 1 to 4 solutions, there is a decent jump. However, as you manage to sample more solutions, while the gains do increase, they appear less and less marginal. What's interesting is that with All-Star Math, even with fewer sampled solutions, it manages to perform much more effectively than many other models. It's really surprising that just by sampling more solutions and processing the information differently, the model manages to achieve higher levels of reasoning. Something that stands out even further is that the All-Star Math model actually performs better than the 72B model. This just goes to show that this method is highly effective. Using Monte Carlo Tree Search and the process preference model demonstrates an approach that may be worth exploring for larger models. Now, as I'm diving deeper into these research papers, I'm starting to see that claims of superintelligence might not be that far-fetched. When we look at this, the ability to achieve such high accuracy with fewer sampled solutions makes All-Star Math really cost-effective and scalable, particularly for tasks requiring mathematical reasoning. I found in the paper was that it also generated its own data as we spoke about, but the crazy thing about this was that its own generated data was better than GPT-4. We can see here that it says even randomly sampled code-augmented chain-of-thought solutions from our small language model yield comparable or better performance than GPT-4 synthesized NummaMath and MetaMath datasets. This indicates that our policy SLMs, after rounds of self-evolution, can generate high-quality math solutions. It says these results demonstrate the huge potential of our method to self-generate higher quality reasoning data without relying on advanced LLM distillation. And this is basically incredible. This statement refers to the randomly selected reasoning paths generated by the model during training. Even without selecting the absolute best solutions, all of the random samples, these ones, are much higher quality. That's pretty crazy because NummaMath and MetaMath are essentially synthesized by GPT-4, which is a much larger and more powerful model. These datasets, NummaMath and MetaMath, are considered high-quality datasets. So when we talk about surpassing them, that actually demonstrates the strength of All-Star's math, the self-evolution process, and the quality of these reasoning solutions. This isn't just luck. This is the result of self-evolution. Through the iterative rounds that we talked about, these 4 rounds, the SLM becomes skilled enough to generate solutions that rival those produced by an advanced model like GPT-4. This is absolutely crazy. We are now breaking the dependency on large language models. We have to think about this. Let's say we had a model that was much bigger and we were able to generate methods that were smarter than smarter models from the future. I know that sounds like it doesn't make sense, but when we look at how we're taking a 7B model and making it generate things that are smarter than GPT-4, which is a 1.8 trillion parameter model, we can think, okay, what if we have a much larger model and focus on making that one using these kinds of methods to improve itself iteratively over time? When we actually take a look at what that means for the future, that is going to be crazy. Now, something crazy about this paper as well was that they spoke about how there were emergent capabilities. Emergent capabilities in AI are essentially capabilities that arise without prediction. So these capabilities arise without training them, without specifically wanting those capabilities, or without thinking that the capability may arise. We can see here that they put in Chapter 5, in the findings and discussions, that there is the emergence of intrinsic self-reflection capability. It says a key breakthrough in OpenAI 1 is its intrinsic self-reflection capability. When the model makes an error, it recognizes the mistake and can self-correct with an answer. Yet, it has consistently been found to be largely ineffective in open-sourced LLMs, which are, of course, the models that they're using right now, the F series and the Quinn series. It says the community has actively explored various approaches, including self-correction. This is where self-correction and, of course, self-reflection come into play. To explicitly train or prompt a language model, LM, to develop such capabilities, researchers often use other models to try and standardize this way of thinking. However, in their experiments, they unexpectedly observed that our Monte Carlo Tree Search-driven deep thinking exhibits self-reflection during problem solving. As shown in Figure 4, which I'll display shortly, the model initially formalizes an equation using a specific approach during the first 3 steps. This would have led to an incorrect answer. But in the 4th step, the model recognizes the low quality of its earlier steps. Rather than continuing along the flawed path, it backtracks and resolves the problem using a new, simpler approach, ultimately arriving at the correct answer. What's fascinating is that we can see this process in action. Here, the model initially works to solve the problem, makes an error, and then engages in intrinsic self-reflection. It thinks outside the box to find a simpler solution. As the image progresses, we can see the PPM, predictive processing model, scores initially reflect negative values. However, as the model adjusts its approach, the PPM scores increase, signaling improvement. Interestingly, no self-reflection training data or explicit prompts were provided in this process. This suggests that advanced System 2 reasoning fosters intrinsic self-reflection naturally. This realization is groundbreaking. Consider this. They've managed to get a small language model to achieve the math reasoning capabilities of OpenAI 01 using a process that essentially combines search and compute during testing. Through iterative evaluations and multiple sampled solutions, the model continually improves itself. Now imagine the possibilities when we scale this up. With larger models and significantly higher compute budgets, we could develop systems so advanced we might not even fully comprehend their potential. This raises incredible prospects for the future. It's no wonder why certain individuals at Microsoft in recent interviews have suggested that we could achieve fully self-improving AI by 2030.
That's a narrow version of AI when we use it for a specific purpose, right? A more general AI is going to be one where it has things like recursive self-improvement. It could edit its own code in order to get better, or it could self-improve, or like it would have autonomy. It could act independently of your direct command, essentially, or you give it a very general command, and it goes off and does all sort of sub actions that are super complicated, like, maybe even invent a new product and create a website for it and then set up a drop ship for it and then, go and market it and take all the income and then do the accounts and so on. I mean, I think that's kind of plausible in, say, 3 to 5 years. Before 2030, I think we'll definitely have that, and might well be much, much sooner.
I think that when we actually look at this, the conclusion here states that RAR Math, a self-evolved system with a deep thinking approach, significantly boosts the math reasoning capabilities of small LLMs, achieving state-of-the-art OpenAI level performance. Our approach demonstrates that small LLMs can self-generate high-quality training data for frontier-level math reasoning, and this is absolutely remarkable. Extensive experiments across 4 different sizes of small LLMs and challenging benchmarks demonstrate the superiority of RAR Math in achieving leading results while outperforming existing math reasoning LLMs and best baseline models. We also reveal key findings, including the emergence of self-reflection and the effectiveness of process preference modeling, PPM, in identifying critical intermediate steps, such as theorem application steps. Finally, RAR Math can achieve further improvements by collecting more challenging problems, and we leave this as future work. When we consider what we've just read here, it's truly remarkable. The test time compute paradigm is clearly real. Having a model sample more solutions and search through those solutions is undeniably the next paradigm. OpenAI has spoken about this in great detail. And when we applied this to a 7 billion parameter model and used PPM to identify the key steps, we observed an incredible enhancement in model capability. The model was generating synthetic data that surpassed the quality of data available from GPT 4.0. Remarkably, this approach even outperforms model distillation. So yes, while this is an area of significant advancement, the only caveat is that it's currently limited to math. However, the discussion on generalization is also noteworthy. They mentioned that RAR Math offers a general methodology for improving LLM reasoning applicable to various domains. Specifically, RAR Math can generalize to more challenging math tasks, such as theorem proving, even though its current focus is on word problems due to dataset limitations. Nonetheless, RAR Math demonstrates the potential to prove mathematical statements. As shown in Appendix 8.2, it successfully proves an Olympiad-level problem involving Fermat's Little Theorem, providing a step-by-step correct proof through its deep reasoning process. Now, this bit right here is just pretty crazy because a mathematical theorem step-by-step actually requires deep reasoning, logical consistency, and advanced understanding. Most AI systems, they actually struggle with such a task because they require logical deductions and not just memorization. They involve multiple layers of reasoning to connect abstract concepts. And the fact that RAR Math can handle a proof of an Olympiad-level problem like Fat's Little Theorem suggests that it isn't limited to solving straightforward computational problems, but can construct complex proofs reflecting reasoning akin to how humans approach mathematics at a high level. Now, traditionally, AI systems, they've really excelled at solving structural problems like word problems with clear answers. But for this model, when we actually take a look at things, it's actually taking it a step further by showing it, it can handle formal proofs that involve logical rigor, abstract reasoning, and a need to justify every step mathematically. So this transition is somewhat of a paradigm shift. And it's a paradigm shift in terms of what these smaller models can achieve, rivaling the capabilities of larger, more resource-intensive models. And when we look at this second part right here, it talks about how this model is able to generalize to other domains, such as code and common sense reasoning. And it says notably, synthesizing step-by-step verified training trajectories for general reasoning requires a mechanism to provide feedback on whether a given trajectory reaches the desired output at the end of the multi-code research rollout. For instance, in code reasoning, this could involve designing extensive cases. In general reasoning, feedback could be obtained through human labeling or mutual verification with another LM. So this is pretty impressive because code reasoning, requires understanding syntax, logic, and problem solving all at once. And if this system is optimized for math and it's able to be optimized for other domains like programming, this is going to be a leap in versatility. And they're basically stating that, if this is able to generalize to code reasoning, it could be able to write a function or script step by step, then run test cases to check if the function works correctly and improve its reasoning based on the test results, just like it validates the math solutions using Python execution. I do have to say, though, that would be particularly difficult because one thing that was being discussed on Twitter the other day was that it's quite hard to get correct answers for questions that don't really have a definitive answer. But whereas math, where you have a definitive correct answer, it's quite easy to get verifiers for that. And common sense problems are a bit more open-ended. But at the same time, this is incredible research that shows us that we are clearly, every single day, edging closer towards AGI. But at the end of the day, I still find this completely crazy because when we think about this, when you look at the overview of the system, it is math that underpins many other things. Once you're able to truly solve math, which we know the OpenAI's GPT-3 model was able to do really well at math and get 25% on pretty much an unseen benchmark, although that training round cost, I guess you could say the inference time was around 1 million. Do I think we can understand that the trajectory of these models now is going to be something that's absolutely insane? And this is why people are so bullish on artificial superintelligence. It's because in early research papers, these researchers were stunned. One of the things they realized was that these graphs, like these numbers, weren't going down. They just kept going up, as long as you managed to sample more solutions. So over time, as long as we manage to sample more solutions and get more effective at learning how to identify the correct reasoning steps, I don't think there's going to be a problem that these models aren't going to be able to solve. And when we understand that paradigm, we can understand that maybe those talking about artificial superintelligence aren't that far off after all.
I think both Demis and I believe we are going to get superintelligence. It's not hype, and it's not designed to distract from other problems with AI. It's what we have believed for a long time. Now, I thought it would be much further away, but the speed of recent developments means I think it's going to be quite soon. I think between 5 and 20 years, I think Demis thinks in about 10 years, we'll get something like superintelligence. And we have to worry seriously about how we stay in control then.